Bien, je vous propose de démarrer le séminaire d'aujourd'hui. Le séminaire d'aujourd'hui est tout à fait exceptionnel puisque nous avons un visiteur de Berkeley qui est venu spécialement pour nous. And so I'll switch to English to thank you very much for being with us today, Steve. Steve Piantadosi comes from University of Berkeley, where he just founded the Computation and Language Lab. And Steve has been instrumental in developing a new vision of infant development and also adult brain computation and psychological computation, which is the idea of a language of thought. I told you in the past years in my different courses about the work of Josh Tenenbaum. And Josh Tenenbaum is a pioneer in artificial intelligence and the comparison between what can be accomplished by algorithms and in AI and by the human brain, with the idea that the human brain still has a lot more in store than just the neural networks, the artificial neural networks that we see, which are so successful these days. So Steve Piantadosi got his PhD with Josh Tenenbaum at MIT, also with Ted Gibson in linguistics. So he's at the border between linguistics and this more computational approach of the mind. And then he moved to Rochester, where he did his postdoc with Dick Aslin, and finally, more recently, I think less than a year ago, moved to University of Berkeley. He's going to tell us today about the hypothesis of a language of thought in infancy. Thank you very much.
Great, thank you. Thank you, and thank you very much for inviting me to come talk and talk to everybody. So I'm going to be giving a kind of overview talk of a variety of projects that I've done with a number of collaborators and students in my lab have done that are all aimed at sort of evaluating and developing the hypothesis that thought looks in some ways like a language. And I'll tell you exactly what that means and exactly what the tests and predictions look like. This is in contrast to other kinds of approaches like neural networks, and I'll give you the sort of details of what the representations are likely to look like, or the kinds of representations that we'd like to evaluate. So in this talk, I'd like to start just by giving you a general overall motivation for why we even think like this, why we would even consider this as a hypothesis. I'll tell you more specifically what the hypothesis is of a language of thought, and then I'll focus on 3 different experimental domains where we've tried to evaluate this. The first is a collection of experiments with adults where we teach them essentially new concepts, and then we try to model what their learning looks like, their learning acquisition trajectories, as well as their patterns of mistakes, with models that have a logical language. And I'll show that works very well in predicting what kinds of generalizations and responses adults give. Then I'll talk about some work with children and infants aimed at testing the kind of more basic assumptions of a language of thought, in particular compositionality. And finally, I'll talk about some experiments with children, adults, and primates aimed at evaluating the kind of hierarchical biases that we think would underlie a language of thought. And finally, if I have time, I may go through the last section pretty quickly. I'll talk about some computational work that we've done, trying to think of what a language of thought might be like, how it could support development and learning of a broad array of different kinds of representations and processes. So let me start with the kind of general motivation for this way of thinking. Motivation is actually very simple. There's a very simple observation behind it, which is that adults, humans, have very broad knowledge of algorithms and processes. So there's lots of different kinds of things and lots of different kinds of structures that we can talk about. So just to pick a simple one, on the bottom right here, you might know how to tie a tie, right? That's a process involving some pieces of cloth. You know what that algorithm is or what that procedure is. You might know even more complicated kinds of procedures, like how to solve a Rubik's Cube or how to solve a 11 by 11 or 12 by 12 or whatever that is, Rubik's Cube. People who study these things come up with very sophisticated internal mental models and mental representations for how to deal with this. Everybody knows this is a kinship tree, right? Everybody here knows the meanings of words like uncle and grandparent. And what's notable about those word meanings is that they essentially correspond to a kind of structural relation or a very little process that happens on a family tree. right? I could say, well, my grandfather's nephew, right? And you could figure out how to compute that on the family tree. So what you know about those words and what you know about those meanings has to deal with that kind of structure. Maybe more generally, people can learn counting, you can learn mathematical systems. In some cultures, you might even learn a body counting system. So this is a body count system from Papua New Guinea, where people in that culture will learn to count all the way through from one side of their body to the other. And what's interesting is they learn not only that mapping from body parts to numbers, but they also can learn and can, in some cases, infer different kinds of algorithms, like how to do addition or multiplication in that kind of system. So the point of all this is that there's lots of different domains. You can think of mathematics or music or computer programming where people's knowledge seems to be in some sense unbounded or unlimited, right? We know a huge variety of different kinds of structural processes. And this raises a big challenge or a big question for cognitive development, right? Which is, how do you start from whatever it is that an infant starts with and end up with all of these different kinds of representations and processes, right? This is a hard challenge for development because none of these things, well, at least most of these things, it's not clear that they're evolutionarily relevant in any way, right? So we probably don't have built-in innate representations for how to solve a Rubik's Cube or how to work with a body counting system. And so whatever it is that a baby has, they have to be able, whatever representations a baby is born with, right, it has to be able to learn a huge variety of different types of other representations and other kinds of structures. And so this general motivation has led some people to hypothesize that, in fact, what the representation system looks like is much more like a programming language than you might think looking at neural networks or kind of classical cognitive psychology. And the reasoning is that in many of these domains, we can write down programs as procedures for how to solve different problems. And so if learners can figure out how to make learning work over program-like representations, then we potentially have a theory to explain how you can conceivably get such a wide variety of different structures and representations, in the same way that you can write down a huge variety of different programs if you have the knowledge of the sort of pieces of the programming language. Perhaps what kids are born with are the pieces of the programming language, and what they do over the course of development is put those pieces together in order to accommodate whatever kind of representation or structure they're faced with in the world. So let me give you a more concrete example of this. This is a study in 2000 by Jacob Feldman, and it actually, I think, started a bunch of this work on the language of thought and led to a lot of it being taken more seriously in cognitive psychology. So what Feldman did was give people different rules to learn. So you can think of an example like I'm going to try to teach you a new word. Maybe that word is Daxi. And secretly, I know that something is Daxi if it's red and a circle. Okay, so I might show you a bunch of shapes of different colors and tell you that some of them are Daxi and some of them are not Daxi. And you look at each of these examples of shapes and try to figure out what Daxi means. Right? And if I show you enough of them, you'll eventually come to figure out that Daxi means red circle. So what Feldman did was vary the complexity of the target rule, right? Vary the complexity of what Daxi means. So for instance, you might think of something very simple, like Daxi just means red. You might think of something really complicated, like Daxi means a red circle. Or you could build up to even more complicated kinds of target concepts. These are never shown to participants. All that's shown to participants are examples of shapes. And what you measure then is how hard it is for them to learn each of these as target concepts. So this complex one is really complicated, right? It has a bunch of different logical operations and a bunch of different features of things. So an object is Daxi if it's a red circle or it's a square. That's very complicated compared to Daxi just meaning red. What Feldman then measured, so on the x-axis here is complexity. That's just the number of operations. And on the y-axis is just people's accuracy on learning this as a target concept. And what he showed basically is that as complexity increases, so as you go to the right on this plot, people's accuracy decreases. So you might have thought that these kinds of logical descriptions, right, had nothing to do with psychology. But in fact, the complexity as you measure it in a logical description seems to be a very strong determinant of people's ability to learn different representations or to infer them from data. This plot is actually bigger because the kind of original study broke this down by how many positive examples there were. So you want to be sure that, for instance, this complicated one, maybe there's fewer positive examples than there are of just red ones. And so this plot is broken down by the number of positive examples and the number of features that you study. But you can see that within kind of any of those groups, you find a strong relationship between logical complexity and people's ability to learn concepts. So these kinds of representations have a couple of properties which I think motivate thinking about a language of thought. The first one is that they're built compositionally from simpler pieces, right? So this concept, if DAXI means, red and circle or square, that's built up out of concepts, simpler concepts like or and red and circle and square. This property of putting things together, putting together simpler pieces like that, right, is exactly what you find in other domains like programming languages, right? This is how Python or C++ or something works. Or also human languages, right? This is how sentences work. We put together individual words into sentences. Combined with this, combined with this compositionality, there seems to be just a psychological preference for simpler kinds of concepts, right? So people find it easier to learn when there's a shorter logical description length. So just to be clear here, the hypothesis is that what's going on when people are doing this kind of learning, when they're in this kind of learning setup, is that they're literally composing logical operations like these, right? So they're mentally forming in their minds those kinds of theories about what DAXI might mean, and evaluating those hypotheses. And if you have a bias for simpler things, then you can think of that as a kind of Occam's razor, right? It says, with just a little bit of data, if my data is ambiguous, I should prefer simple concepts like red and red circle, and it should take more and more data to convince me that it's things like red circles or squares. So the kind of working hypothesis of what I'll talk about is that learning works in exactly this way across development. Okay, that's the hypothesis. So you can think of this as learning as sort of like a statistician programming. Learners compose operations in some kind of mental representation in order to form generative models or explanatory theories of data that they observe. And so just to make this a little more clear, programs are written in a language of thought, right? A language of thought in the Feldman example might be logical operations, but in other examples that I'll talk about later, there's other kinds of mental operations that we think are relevant. Nature provides the primitives, meaning the pieces that you compose together, and the inference mechanisms, right, that say, given some data, how should I figure out which composition of pieces to form? But depending on what input I get, I'm able to use those built-in operations and the inference mechanisms in order to learn specific representations in specific domains. Okay, so this kind of general idea is one that we've applied across a number of different domains. I'll just put up a kind of general overview slide of this and just point to a few examples. One of them is learning counting. So we have a kind of learning model that takes observations of where parents say different number words and figures out the algorithm behind counting. And that algorithm is structured in exactly this way, right, where it's composed up of simpler kinds of operations that you might do to things in sets. There's learning models that look like this for natural language semantics. So if you look at words like every and most, right, how do kids learn what the word most means? There's no most out in the world. Most is a kind of abstract procedure. It has more abstract semantics, and you can learn it using exactly the same kinds of tools and techniques as in the Feldman study. Other people have applied this general idea to other kinds of things like learning kinship, or learning handwritten digits. So Brendan Lake had this very cool paper a few years ago showing basically that you can model people's acquisition of sort of digit-based concepts. So like, what does the letter P look like? Letter and digit-based concepts. Using the same kind of generative program, so putting together pieces that correspond to strokes and smaller structures. And there's other work from Josh Tenenbaum's lab looking at learning, sort of formalizing the idea of learning things like concepts of magnetism, right? So what do we know about magnetism? Well, we know that two positives attract each other, and two positives repel each other, and a positive and a negative attract each other, and that some things are magnetic and other things are not magnetic. Your kind of intuitive theory of magnetism is one that's very easy to state with a logical language, right? You could sort of translate what I just said into first-order logic, for instance. There's work by Tomer Ullman and Josh Tenenbaum essentially showing that you can model kids' acquisition of that concept, their acquisition of how magnetism behaves, using exactly the same kind of formal setup as the Feldman study I talked about, right? Okay, so all of these are cases where learning looks a lot like programming, right? The representation that you want to arrive at the end looks like a sort of structured, logical thing, and we can model it by thinking about learners as beings that discover programs from data. So they look at some data, just like you might look at the positive and the negative examples in the Feldman study, and they try to figure out the abstract rule behind it. So I wanted to talk about three specific areas where we've looked at first learning, so sort of a fancier version of Feldman, and then tried to evaluate the more basic assumptions of this kind of approach and this way of thinking. So the first kind of predictions of this language of thought approach, I should say I'm not going to talk much about the Bayesian side of it, but behind all of these models are kind of Bayesian statistical inference models that make everything a kind of correct and coherent statistical inference. So you can say, given some amount of data, what's the most likely kind of logical structure to have generated it behind the scenes. So the first kind of prediction that I'll talk about is that, you know, if this is a good approach generally, right, then we should be able to find hallmarks of this kind of learning in different domains and for other kinds of representations. So one of the things we were interested in doing was taking Feldman's kind of study and evaluating what happens when you move to a domain which is richer or fancier than just simple Boolean logic. So our experiment otherwise is structured very similarly. Let's see here. So we showed people collections of objects and told them that, well, what makes an object DAXY might have to do with the features of an object, or it might have to do with the other objects that are in a set or a collection. And then we recorded people's generalizations as they went through an experiment, getting feedback on each item. So initially, you don't know what makes an object DAXY, and so you have to guess. And after you guess, I give you some feedback. So I tell you that in this first set, this one was DAXY, this one was not DAXY, and this one was DAXY. Now, given this, tell me which of these objects are DAXY. So how many people think that's DAXY? And how many people think this guy is DAXY? No. Okay. So people make some generalizations. In this example, people tend to think this one is DAXY and this one is not DAXY. And then I tell you, no, actually, in this set, both of these happen to be DAXY. Now, DAXY always means the same thing. Okay, so now your goal is to look at this example and tell me which of these happen to be DAXY there. Okay, so how many people think this guy's DAXY? How many people think that guy is DAXY? How many people think that is? Yeah. Actually, none of those are DAXY. Okay, well, we'll just do one more here. So just think about this for a minute. So hopefully, as you're going through this, you can feel yourself thinking of different hypotheses and kind of evaluating them against the data, right? This is, in some sense, I think the best kind of intuitive evidence for a language of thought. The hypotheses you're thinking of are probably linguistically structured in some way, right? You're thinking like, okay, DAXY might mean, you know, red unless there's a triangle or something, or red and not yellow, or I don't know. So how many people think this is DAXY? Yes? How many people think this is? Yes, okay, oh good. So you guys probably have learned some kind of logical rule. There's actually, of course, infinitely many which are consistent with this, but one that people find very intuitive is that an object is Daxy if there exists another object of the same shape, right? So here the red guys were Daxy because there's another object of the same shape, but here you would think nothing was Daxy. And what's interesting is that as you progress through this experiment, because we're gathering incremental predictions, like I said, you feel like you're sort of switching hypotheses and changing your mind about it. Many people after this first example probably thought that Daxy either meant red or it meant square, right? That, you could have come up with this rule right from the very beginning, right, if you were very sharp. I think I had a linguist once do that in a talk. But most people think that this is way too complicated to explain just this first data point. And so that right there is the kind of Feldman bias of people preferring to think of simpler logical explanations as opposed to more complicated ones. But critically, if I give you data which supports something much more complicated, right? Supports something with a quantifier where I have to think about the properties of an object in relation to the other properties in a set. People are totally happy to discover that from just a couple of examples, like many people here did. So what we did in this learning experiment was essentially give people a ton of these different kinds of target concepts. And so some of these are these kind of simple Boolean things like blue or green. Some of them are things like the unique largest blue object. Some of them are ones like the one that you guys just learned. And some are even more complicated, so things like the same shape as exactly one other blue object. And the point is not so much about each of these individual concepts, right? These are just kind of logical concepts that we use to construct stimuli to give to people. The point is what specific patterns of generalization do people make as I give them more and more data like this. So let me just show you an example of this. On the x-axis here is how many sets people have seen. So what response number are we on going throughout the experiment? And on the y-axis is accuracy. And essentially what you can see is that for most of these, people are shown in black. For most of these, within about 20 or 30 different items, people are happy to learn these kinds of concepts, right? So they reach accuracies which are close to 100%. What's interesting, though, is that along the way, they often make kind of systematic patterns and mistakes, right? So here we're learning a concept, circle or blue, and you can see that there's a place right here where people systematically get it wrong, right? They only get it right 30 or 40% of the time. Here's another place where people get it wrong. So those correspond to specific items in the sequence of shapes that I'm presenting to them, where people tend to generalize in the wrong way. And what's important is that what it means for them to generalize in the wrong way is just that they don't generalize according to the correct target concept. So they don't generalize according to circle or blue. But it turns out that what they do correctly is they generalize according to some other kind of concept which is so far supported by the data. Right? In the same way as right here, after I had just shown you this first set, right? If I answered no to this, right, that would show up as a mistake or an error, a systematic error in our experiment. But it's actually a reasonable inference because the first data point had only told you that the concept was red or was red, for instance. Okay, so you have to be a little bit careful interpreting errors here. Errors in this plot might correspond to totally reasonable inferences that people are making from data. Those are the sort of black dips. What's shown in red is a learning model which is a kind of Bayesian version of a Feldman model where what it's doing is taking the observed data and trying to infer what the unseen logical rule is. And what's notable about the model in red is that it shows similar dips in accuracy on the exact same items as people. It's not perfect. It gets the magnitude wrong a little bit in some places. But the fact that, for instance, that there's a dip in the learning model here means that when people give that response, right, when they make that, quote, error, they're actually making a pretty reasonable inference. They're making the same inference that a smart statistical learning model would have made, a learning model in particular which has a bias for simpler kinds of rules and representations. Does that make sense? Yeah, okay. The second component of this, though, is that because we have this kind of rich behavioral data, and we have learning models which can work over sort of the hypothesis space of logical rules, we can write down different learning models and see which of them correspond most closely to people's inferences. So here's just an example of this. Here I'm teaching people the concept, there exists another object with the same color. Okay, so that's a lot like the one that you just learned. And you can see that, again, here maybe around 40 or 60 items, the black curve people reach pretty high accuracy. But then we can write down different languages of thought, right? One of them just has access to the features of objects, right? So it can learn rules like red circles. And the second one has access to quantification. So it can write down rules like there exists another object of the same color or something, right? So that learning model has access to there exists and for all. And you can see that the full Boolean that's in red, the model which just has access to object features, right, doesn't do very well. It does pretty well in the beginning, but then after about the 20th item, when people really start to figure it out, the red model doesn't do well at all. In contrast, the model which has quantifiers does about equally well at the beginning, and then it can track people as their accuracy increases throughout. Right? So what this means is that we can write down two different sort of hypothetical languages of thought. In this case, it's one with quantifiers like for all and exists, and one without quantifiers. And then we can sort of fully model the learning curves and compare them to people, and therefore make inferences about which language of thought is likely to be the best one. Right? This is some evidence, for instance, that people's space of hypotheses, right, includes quantification. And we've done this a little bit more systematically. I won't go through the kind of details here. I'll just refer you to the paper, but you can basically write down different systems for representing logical rules, things like conjunctive normal form or disjunctive normal form or not and. You can write everything with just an and basically show that it looks like people have access to a large variety of different logical operations and an ability to compose them, as well as kind of first-order operations. So sorry, each of these scores are held-out likelihood scores. So things closer to positive infinity are better. And so that means that stuff near the top of these tables are good models of human learning. They're good representation languages for capturing people's biases in this kind of task. And things near the bottom tend not to be good. Okay, so this is a task that we've been interested in translating to kids, right? Because all of these are studies with adults. It'd be really interesting to know what happens with children, right? Because the main motivation for all of this is trying to make sense of development kind of much more broadly, right, from infancy onward. And so we've done a version of this task with kids that looks like this. So this one doesn't have sets of objects. It just has objects and features. But like the adult data, we can try to model kids' generalization patterns. And I'll just show you the kind of one slide, one figure summary of this. So on the x-axis here is each individual response and what the model thought, how accurate the model thought it would be on them. And on the y-axis is kids' actual accuracy there. And so if kids lie along the line y equals x, which they mostly do, then the model is well calibrated to what kids are doing. And so it looks like the same kind of logical language of thought model can do a pretty good job of predicting the patterns of responses and the mistakes that kids make in learning similar versions of this task. I have to add one caveat here, which is that in order to get a sort of good fit like this learning model essentially has to have very little memory. So in the adult case, we allow it to remember, a couple of the previous examples. In the kid case, if you fit a parameter to it, essentially kids are making inferences from just the previous example or so. And so kids, when they're doing this kind of learning task, it looks like they're able to figure out these logical rules, but they don't have the kind of working memory capacity in order to get things which are much more complicated than this. Okay, so just to summarize, learners' inferences in controlled laboratory tasks follow what you would expect from these kind of language of thought theories, meaning we can model acquisition curves and patterns of mistakes by writing down computational models that do inference over logical rules. In fact, we can reverse engineer the kind of components of a language of thought from behavior, right? Because we can model it, we're able to write down two alternative models or multiple alternative models and see which one best matches people's behavior. Okay, so I wanted to talk next about a sort of even more basic test of language of thought, which is looking at compositionality in children. So the kind of key feature of these kinds of logical representations is that you're putting together pieces, right? You're putting together and circle and square, right? And so that raises a really natural question. Well, can kids put together pieces, right? If you teach kids pieces of things, are they able to combine them? Or do kids need instruction on combining them, right? You might think that this mode of thinking is not very natural. Maybe it requires very advanced language or explicit instruction or something like that. What we did to test compositionality was the following. We essentially taught kids two different pieces. So what they observe here on the top is they observe a car going behind a screen. And that screen has a blue icon on it that basically tells kids that it paints it blue. So a car goes, gets painted blue, and then comes out the other side. That's one piece. Then we taught them a second piece. So here's a car, goes behind a screen with dots, and this screen changes its stars to dots. So it comes out on the other side with dots. So now I've taught you two pieces. Here, pretend you're a 3-year-old in this experiment, and you've gone through and you've learned what each of these screens do. The question then, right, is are you able to make the right generalization when I now put these things together, right? You could think, well, this is almost stupid. It's so easy, right? And it's so easy, right, for us because we're adults and we have compositionality. We know how to put together pieces like this. But it's not really obvious that a 3-year-old knows this. And in fact, if a 3-year-old doesn't know this, then that's probably bad news for a language of thought because the primary way you build structures and things in a language of thought is by composing or putting together pieces like this. In this critical test condition, right, they've never observed a car pass behind both things. Are they able to make the right predictions or not? So here, just to show you, on the y-axis here is the kid's accuracy in one-box training. So this is on the first two conditions that I just showed you. So they're not great at this. I mean, they're 50% or so accurate, but chance is very low because there's 4 different options. So chance is 25%. And it turns out that on the 2-screen cases, they're about as accurate on the one as on the 1-screen cases. Okay? So what this means is that they essentially, like, if they learn these top things, which only about half of kids will, then they get this one totally for free, right? They're totally fine on their own putting together pieces like that. So essentially, conceptual combination through composition it happens for free by this age. What we're really interested, though, is infancy, right? Are infants able to compose things or not? And so we took this experiment and translated it down into an infant task. The difference with infants, of course, is that they can't give you explicit responses in the same way that 3-year-olds can. And so everything has to be interpreted through a kind of looking time measure. So here's how this looks. Infants see a display that looks like this. Then they see this block slide into the path, and this guy goes back and forth here. And when he slides through, he gets painted, just like the cars got painted. This block might then slide out of the way. This one slides in the way, and now when he goes through, he gets painted red. Okay, so there's 2 different functions that are doing 2 different things. You can see also that we changed one aspect of this from the older kid experiment, which is that the features which change are completely separate, right? So there's dots in one area, and then there's redness in another area. And then, of course, the question is what happens, what do infants expect when you put both of these now in the path, right? And you could think of 3 kind of likely possible outcomes that they might expect. They might kind of correctly compose, right? So they might expect that both operations will have applied because the thing will have gone behind both of them. You could think, okay, well, maybe like what mistakes could they make? One possibility is that they might only expect the first function to apply. Another possibility is that they might only expect the second function to apply. Or you could think of others like they might just say this is way too complicated and not show any kind of systematic patterns. But like I said, though, this is an infant experiment, and so you don't get to ask them what they think is going to happen. What you have to do is show them each of these different outcomes and measure their looking times to them. And then we use looking times as an index of kind of how surprising an outcome is. So if you show them something and they stare at it for a long time, that's typically interpreted as them being surprised by that as an outcome. So I can take each of these kind of possible interpretations and translate them into looking times. Here's kind of how things look here. So if I expect only the first thing to happen, then when the first thing happens, I'll look for a very short amount of time because I expected it. If I show you the only function 2 outcome, that's really unexpected, right? And so I should look for a really long time. Because if I expected this and you showed me this, right, then this would be really, really different from that. And so I should look for a long time. And if you show me this outcome, the correct outcome, well, this looks a little bit like that, right? Because it has a red border on the outside, and so maybe I'll be a little bit less surprised than if you just showed me the second outcome. And so you can work through that kind of logic for each of, for infants who would expect the first or expect the second. If infants are correctly composing, then I might expect something like this, where when I show them the correct outcome, they look for the shortest amount of time, and if I show them either this outcome or that one, they'll look kind of equally long at both of them. Let me show you what the actual data looks like. Data looks like this. So here's on the y-axis is looking time. The bars here are means, and the dots are individual infants. Triangles are medians here. And you can see that infants are least surprised by the second outcome when they're shown that. Okay, and they're most surprised by the first outcome, and they're maybe a little bit less surprised by the correct outcome. So what it looks like here, sorry, I forgot to say this is 9-month-old infants. So what it looks like is that 9-month-old infants are not happy to compose operations and put them together in the same way that 3- and 4-year-olds are. In fact, what it seems like is that when they have 2 operations like that, they tend to think that only the second one will have applied. Okay, so the summary here is that this kind of composition is not apparent in very early development, meaning 9 months or earlier. It's actually very plausibly due to memory limitations, so limitations with tracking and representing multiple operations. That's just hard, and it turns out there are other experiments, mainly from the sort of domain of object tracking and early number, where doing multiple things to a representation is really hard for infants to keep track of. So for instance, I think a 6-month-old infant is happy to do a 2+1 addition, right? So you can hide 2 objects and then hide 1 object, and they will correctly expect that there are 3 objects there. However, the same infant is really unhappy to do a 1+1+1. And so you might think, well, what's the difference, right? I'm always dealing with quantities that are 1, 2, and 3 there. And the difference is that 1+1+1 requires me to update some representation 2 times, right? I have to effectively compose different operations, whereas a 2+1 is just 1 operation, right? I just have to update my representation of some objects just once. That's essentially a working memory limitation, and it's very likely the same thing as what's going on with infants in our study here. However, this ability emerges in some capacity by 3 to 4 years old. So it may not make sense to think of the very earliest learning in terms of this kind of compositional hypothesis testing, but certainly by 3 or 4, this kind of general approach might make sense. Okay, so I wanted to talk very quickly about kind of hierarchical biases in children, adults, and primates. This is work that, let me just put this up. So, I talked some about kind of what operations we should think are here, whether there should be quantifiers or not, about testing compositionality, like putting together these kinds of pieces. There's another feature, though, of these kinds of representations, which is very interesting, especially from a kind of linguistic perspective, which is that these representations are essentially hierarchical, right? I have to be first computing, and of red and circle, and then the output of that gets sent to the input of or, right? And the output of square of x gets sent to the input of or. And so these things, these as functions essentially form kind of nested trees. And one kind of interesting hypothesis is that people find these kinds of trees or these kinds of structures just very natural things to process. That's at least a consistent idea with these kinds of language of thought models. And so one of the things we were interested in testing was how natural that is, right? Do people naturally form those kinds of nested hierarchical structures? And in particular, do people from all cultures or all ages do it? And when they do it, do they look different from other species, right? For instance, different from primates. So this is a task which we did, which is modeled on kind of primate ordinal ordering tasks, which looks something like this. So what people and primates and everybody are shown are displays that look like this. And what they have to learn is to hit those parentheses in a specific order. So you learn that when you see these things, you might hit this open, this close, this close. And they appear at random positions on a screen, and your job is just to hit them in a particular order. So here, this corresponds to this training list. Right, so when you see these 4 particular parenthesis types, you always have to hit them in that training list order. And there's a second training list, which is this one, and you also have to learn to hit this one in this order. Okay, so then after people or kids or primates learn both of those training lists, we give them generalization trials where we put together pieces from the inside of the training list and see how they generalize, right? See what kinds of structures they kind of naturally induce. So in this transfer list, I might give you just these 4 inner parentheses and see what kind of outcome you produce. And you can think through that there's a couple of different kind of plausible, likely ways of doing this, right? One of them is to give an answer that looks like this. We call this a recursive or a nested one because I've put the brackets, I put the red brackets inside of the orange brackets completely. An alternative, though, would be to swap these last 2, right? To do open, and then this close, and then this one. And it turns out that the average positions of each of those parenthesis pieces are the same between both of those. We call that a cross dependency because the orange open to the other orange open here is crossed with this open and that one doesn't obey this kind of nice hierarchical structuring that this one does. Does that make sense? Like that. Okay. So we can therefore use that kind of generalization, right? We can use we can use how people generalize on these transfer lists to index how natural it is for them to think in terms of these kinds of hierarchical compositions, essentially. So we ran this task on 4 different populations. The first was primates. These are macaques in Jessica Cantlin's lab. The second was kids. So these are just U.S. children. U.S. adults, undergrads at the University of Rochester, and adults from an indigenous group that we work with called the Chamane, who are from Bolivia. And what's interesting or sort of notable about them is that they have highly variable rates of education. So you can effectively find Chamane adults who have no education, and so it's interesting to know whether their generalization patterns look like US adults, right? That allows us to sort of disentangle education from other effects. Let me just show you a video of a macaque doing this. So he gets a little reward every time he gets it right. And there's mixed in there some kind of basic training trials like those, right, which are, yeah. Okay, so hopefully you get the idea. Now let's look at what responses people give. Okay, so here are the kind of 3 primary kinds of responses that we're interested in. The first is these recursively center-embedded ones, right? Those are ones that respect the hierarchical grouping structure. The second are the crossed ones, right, where I open, and then I close the first one before I've closed the second one. So that's like not a correct use of parentheses, and it's not correct because it doesn't respect the fact that parentheses are really representing groupings in some sense. And finally, I didn't talk about this before, but you can give, this is also a perfectly valid response, right? I can open and close each of them. And this one is not very interesting because it doesn't tell us anything about whether they like hierarchies or not, right? Really, the contrast between these two tells us how much they like kind of correct hierarchical grouping structures. So what's shown on the y-axis here is the proportion of responses that people give to each of these. And you can see that for US adults, they overwhelmingly like center-embedded structures. Okay. The question is what happens for everybody else, where here's Chamane adults. So Chamane adults also overwhelmingly like center-embedded structures, maybe not quite as much as US adults. Chamane adults like it about as much as US 3- and 4-year-olds. And what's interesting here is that monkeys are basically at chance between these two, right? So on this version of the experiment, monkeys don't really seem to have a preference between center-embedded and cross structures. And in fact, there's lots of other strategies that are perfectly reasonable ways of solving the task as I described it. For instance, if I track the ordinal position, right? If I say, on average, what position did this particular parenthesis type occur in, then because of how the experiment was constructed, both of these should be equally frequent. And that kind of ordinal tracking is something that independently monkeys are good at. People don't seem to think like that, though. People, even 3-year-olds and adults with little to no education, really like these kind of center-embedded structures. The interesting question is whether there's anything that will make monkeys think like people. One thing that turns out will make them think more like people is if you give them additional lists. So this was just on 2 training lists, right? It was just on, let me go back to, just on these 2 training lists. Turns out if you give monkeys 4 training lists, then they start to like so here's monkeys with 4 training lists, then they start to like the center-embedded structures. And actually, there's kind of a boost here in monkeys in these tail-embedded structures. And if you look at it by monkey, it turns out there was just one monkey, Coltrane, who almost always did tail embedding, and 2 others, Horatio and Beyonce, really liked center-embedded. So there's some interesting individual differences, but it's not as though this is a structure that other primates can't represent. It's much more like they're able to do so, they just don't have the same bias, they don't have the same kind of preference for it that humans seem to have. Okay, so these kinds of recursive hierarchical grouping of the type you would need for a language of thought seem to be automatic across humans, across culture and ages. And these kinds of structures or generalizations are possible for monkeys, but seem not quite as natural. Okay, so I thought I might run out of time for my last part, so I'm just going to talk very briefly about it. Is that okay? Can I do like 5 more minutes? Yeah, okay. All of those past 3 sections were just experimental studies trying to target these kind of core components of logical representations. What I want to talk about in the last section is a learning model which is motivated by a language of thought and which tries to come up with a kind of general approach for thinking about what learning might look like there. In particular, I talked about these kind of three predictions of this kind of language of thought, but there's some interesting challenges to think about for this approach. So you might think, well, in a language of thought learning model, what you essentially assume is that there are basic primitive operations, and you compose those together to get more richly structured adult-like representations. What happens if infants don't show the kind of primitives that we think are there, right? A good example of this is logic, right? If you think about and or not for all exists, those kinds of mental operations, it's very hard to diagnose if a say 9-month-old has access to those operations. But what if they don't, right? Where does this leave this kind of theory if it turned out that a 9-month-old couldn't compute for all or negation or whatever? Is there some sense in which they could learn those kinds of logical operations, or are those logical operations just so basic that you could never learn them? This is actually, I think, a fairly deep problem. It comes up not just in logic, but in other areas like number. There's sort of interesting debates in the number literature about whether the kind of core components you need for exact number and counting just effectively have to be innate because they're just so simple. From what basis could you ever learn them? Or if there's some kind of learning model which genuinely could discover those kinds of operations. The second problem is related to this, and it's how do children learn so many different kinds of systems? So I started out at the beginning by talking about all of these different kinds of domains where it looks like we have kind of structured, logical, algorithmic competence, right? Things like kinship systems or learning programming languages or quantifiers in language or how to tie a tie or how to solve a Rubik's Cube. How is it that kids are able to learn such a huge kind of breadth of different representations? And so these problems are one that people in my lab have been thinking a lot about recently. Essentially the working model or hypothesis that we came to was that one way to address these problems is to think about language of thought not quite in the way that I've described it, right, as having some innately meaningful primitives like and, or, and not, but thinking about the language of thought as a kind of learning system which allows you to build other systems, right? It's a system where whatever operations are built in are ones that allow you to construct a model or an isomorphism of some other kind of system that we need to think about. Just to give the cartoon version of this, if you think about a structure that you know like the seasons, right? You know that the successor of winter is spring, and the successor of spring is summer, and the successor of summer is fall, and the successor of fall is winter. You know that logical kind of circular structure. Well, you know, a 9-month-old doesn't know that. So whatever a 9-month-old has, it has to be a system which allows them to, first of all, represent, but second of all, discover that kind of structure from whatever data is present around them. And so what we've been thinking of are essentially language of thought learning models that allow you to write down any kind of, write down and represent any kind of structure. Here's just an example. The particulars here don't really matter. All that matters is that each of these symbols, winter, spring, summer, fall, and successor, get mapped to some expression in a mental language. And it just so happens that the expressions they're mapped to here are ones that obey these relationships. So if I take the successor function and I apply it to the winter function, I'll get out the spring function. I'll tell you a little bit more about this in a second. So the general idea here, though, right, is of thinking of mental representations which allow you to write down and model kind of arbitrary systems. And these ones, it turns out, are written in a representation system that we've been using called combinatory logic. Combinatory logic is a representation system that was invented in the sort of early 1900s by logicians who were trying to figure out how they could do logic without variables. I won't go into the kind of details of that, but you know, in an algebraic expression, if I said like f of x equals x squared plus 3x, right? I have x's everywhere. And those x's end up being a little bit inconvenient because the syntax of what's allowed in my algebraic expressions depends on what variables are there. And this bothered these kinds of early logicians, and so they tried to come up with systems where essentially the representation language had a uniform syntax, and there were no x's ever. And it turns out you can do that. You have to define things called combinators, which essentially shuffle variables around in these kinds of representations. The details in the history don't matter much. All I was going to say is that it was invented apparently independently by 3 different logicians all working in the same era. So it's a useful kind of mathematical tool. Why is it useful for us? Well, it's useful for us because it permits kind of arbitrary computation with only 2 primitives, and both of them are very simple tree manipulations. So I'll just write the first one down. So the first one is called k. K is a constant. So k is a function that takes 2 arguments, x and y, and it just returns its first argument, x. Okay, so if I were to write this in kind of more standard notation, I might write it like this. So k of x, y gives me back x. And the second is a function called s. S is a little bit more funny. S takes 3 arguments, x, y, and z, and it essentially does this tree manipulation where it computes x of z and then y of z. So in sort of more standard notation, it might look like this, x applied to z and y of z. And what these early logicians proved, actually, was that these 2 operations are effectively Turing complete. So they can compute any function. You can take any structure, any representation or algorithm, and translate it down into S and K. It's a kind of minimal Turing complete representation system. And that's really nice for our purposes because it allows us to potentially write down other kinds of logical systems and model them using just S's and K's. So to give you an example of this, if I wanted to write down a theory or a model of Boolean logic and or not true and false, I would map each of them to some structure of S's and K's. And if I wanted to then compute something like what is OR applied to true and false, I would substitute in OR, which is this crazy expression. That's there. I'd substitute in true, which is this one, and I'd substitute in false, which is that one. And then I would just follow those rules, right? So I can chug through each of those rules that I just did. I won't go through all of the details here, but what I end up with at the very end is this, which if you look up in the table is true. Okay? So In other words, by taking this and translating it into the S and K combinators, what I end up with is the ability to compute what the outcome of OR and true and false is, and I get back true, which is the right answer. So maybe you can see why early logicians really loved this, right? It sort of reduces everything to a very simple kind of representation system, and in fact, it shows that you can, what they showed, in fact, is that you can take any kind of logical system like this and translate it into S's and K's, just like that. So this technique for mathematical logic is called church encoding, and it's essentially using one logical system to mimic the behavior of another. So S and K just happen to be such that if we want to write down a model of some other system or figure out how some other system works, if we want to write down a model, we can come up with some S and K structure that will mimic the dynamics of something that we're looking at in the world. If I have a second, I'll just show this. My favorite example of this is the following. There's these communities of people on the internet who like to get old printers like this. Okay. It gets much fancier. It sounds good in a minute. But the idea here, right, is that there's some natural dynamics to a printer, and you can sort of trick the printer's dynamics into doing something else, right? You can trick the printer's dynamics into playing Eye of the Tiger if you want to. And that's exactly the logic of church encoding. There's some natural dynamics to S and K, and if you're clever, you can trick S and K into doing some other computation, like computing Boolean logic or something else. And so if you ever need to remember what church encoding is, just think of that. And so what we have in my lab essentially is a library to infer church encodings from data. I'll probably skip this because I'm out of time. But what this does essentially is observe some relations in the world and try to come up with a church encoding. And if you do that, it turns out to be very easy to discover these church encodings, and you can learn kind of arbitrary structures. So you can learn structures like the natural numbers, or like magnetism, the magnetism example I talked about, or Boolean logic, or quantification, or any of these kinds of domains. And what learning corresponds to is building the right thing out of S's and K's in order to mimic whatever system it is that you're trying to study. So I'll just skip through these. We've done a bunch of kind of micro experiments with them. Okay, so the kind of lesson from combinatory logic is that there's a real sense in which we don't really have to assume cognitive content, right? S and K are just kind of dynamical operations, but what it might be that kids have, right, is a kind of representation language, of course not combinatory logic itself, but something like combinatory logic that allows you from a very simple collection of operations to write down models of any other system, right, to write down something which is isomorphic and to whatever system it is that you're trying to learn about or trying to represent. And so we think of this, I guess, as a productive kind of metaphor for language of thought and learning, right? It's a simple Turing-complete dynamical system which you can model any other. And a lot of what we've been doing recently is trying to come up with good and human-like ways of inferring models from data. Okay, so let me just summarize here. I've charted out some domains of current experimental and computational work on the language of thought, specifically tight LOT predictions in adult learning experiments, more basic kinds of processes like compositionality and structure, and maybe with sort of interesting limitations in infancy on things like compositionality that likely have to do with working memory processes. I just went through very briefly at the end, right, the system called chorizo. I didn't actually talk about it being neurally implementable, but it turns out that because S and K are so simple and correspond to just tree operations, it turns out to be very easy to encode into a neural network. In fact, that's something that people figured out how to do in the 70s and 80s, so it doesn't even require fancy new deep learning. I'd say that generally the kind of aim of this work, at least, is to push the language of thought hypothesis out of domains of philosophy where it's typically been thought about and into experimental psychology and machine learning, and in particular the kind of intersection of the two, where we're using tools and ideas from machine learning to try to make sense of people's behavior in experimental tasks and in the natural world. So let me just end by thanking a bunch of my collaborators here, including Steve Frigno and Jessica Cantlin, Sam Shad and Frank Malika, Jenna Register and Leon Yang, Josh Tenenbaum and Noah Goodman, and Dick Aslan and Holly Palmieri. Thanks.